Welcome to the second assembler lecture. In today's lecture, we're going to be covering kind of two topics. We're going to extend our recap of memory mapping such that we understand how single and multi-level paging works. And then we're going to go through kind of the basics of register use and then how we can start making certain move operations work in assembler. So we can start getting into the nitty-gritty of how we can actually code in assembler. So first start is on paging. Now I already alluded to this concept in the previous lecture, but just to make things concrete, let's define what we mean by a page. A page is simply a fixed length, contiguous block of virtual memory described by a single entity in a page table. So in many regards, a page is our indivisible unit that we work with during memory management. Contiguous meaning that any byte adjacent to another byte is adjacent to that byte at both logical and physical address space. Now, you see here that we say it's usually the smallest unit which we work with in a memory management system. Now, it is in principle possible to do memory management at a byte level or a word level, but modern operating systems utilize the paging system, so we always utilize a page as our lowest or smallest indivisible unit of memory. Now, in our case, we will consider 4 KB pages, so 4 kilobit pages. That's the standard in Linux. And the exception of that is that, obviously, the kernel, as I mentioned before, has 2 megabyte pages, but we're going to focus on the 4K version. Now, one question we didn't really kind of recap previously is, how do we actually do the conversion from a virtual address space to a physical address space? Last time, we kind of had it done via magic, and then we added the offset to the post-conversion address, but we didn't really discuss how I go from virtual to physical address space. So we're going to cover that in this section. So the simplest way in which we can handle this conversion process is to use what we call single level paging. Now, just so we are all on the same page, is on the left here is our virtual memory or virtual address space. So in this example, it's not a very large virtual address space, it's only 64K. And the X's indicate that that block of virtual memory is not actually being used. So we say it's basically an empty block and nothing has been stored in there. Then we have numbers present in some of these pages, and they basically correspond to the location of that page in physical memory. So in this situation, you see that we have the index 7, and that would imply that it is at location 7 times 4K inside the physical address space. So that would correspond to this 28K to 32K location. Also, you could simply think of it as being as the 8th location, because we index from 0. Either is fine. But for the moment, it's kind of good to kind of remind yourself of this correspondence. So 7 times 4 is 28, which means that the start address of this page in physical memory would be at the 20K mark. Now, if I was, for example, running my program and I needed to allocate more space, and suddenly I needed to maybe read or write to this location over here, what would end up happening is that I would say, okay, cool, I want to get access to that page, but there's an X, meaning it's invalid, so I don't have an address for this block in physical memory. I need to try and load it in. I need to try and allocate some space in physical memory for it. So basically, when I try and access that block, say I wanted to maybe use malloc or something to get access to it, and it wasn't already done so, then I'll get what we call a page fault. So basically, I was unable to find the page that I wanted because of that X. And in that situation, if there's enough space available in physical memory, so say we had an extra block sitting over here, we would simply allocate this new page to that location. So this would, for example, be 8, and we filled it up. Now, obviously, in this exact example, we don't have this space. We're at capacity. So we don't have this extra space. So we need to figure out what to do, because our physical memory is already full. And as much as it would be great if we could just make more RAM, we're often confined by how much RAM our systems actually have. So in that situation, we need to figure out what eviction strategy to use. And by that, I mean, which block in physical memory do we evict? Now note that when this block gets removed from physical memory, it doesn't get deleted. It simply moves to a less fast version of storage. So that in this case would probably be moving back down to the hard disk situation. So it's not lost, it's just going to be slower to access in future. Now the question we actually have to ask ourselves is, how do we decide which block to evict? Now you'll remember that from operating systems that there are a number of ways. For example, you have your LIFO approach, so last in, first out, or FIFO, first in, first out. The most commonly used approach in practice and what's used in Linux is a variant of LRU, which simply stands for least recently used. Linux doesn't use the standard version of LRU. It's kind of a slight tweak on the concept, but it's sufficient to know it's based off of least recently used. Now, the one thing I would like you to try and think at this point is, okay, the system works fine. Seems like we have kind of solved the problem. But there's one fundamental issue that is not properly dealt with, or not so much that hasn't been dealt with in that this approach kind of induces. So I want you to pause the video and think for a little bit, what is the fundamental issue with the single level paging approach? Once you've thought about that again, we can move on to the answer, but I do think it's worth thinking about it for a second first. So the primary issue is that of space. Now, it's not something you might immediately have thought of when you pause the video, but it's actually a substantial hindrance of this approach. So let's use a practical example to see how bad the space utilization can actually be for single level paging. So let's consider the Linux process model, which has a virtual space of 128 terabytes, which we discussed in the previous lecture. So with that in mind, how many entries would we need in our virtual address space? Well, we know our pages are going to be 4K in Linux, so what we need to figure out is a 2 to the 47, which is simply 128 terabytes, divided by 2 to the 12, which will give us 2 to the 35. So that is how many pages we would have in our virtual memory. That's a large number of pages. It's about 34 billion entries, so it's a very, very substantial amount of pages. But we're used to dealing with large numbers in computer science, so maybe it's not that bad if we consider from a space usage perspective. So let's actually figure out how big that table would actually be. Now, in order to figure out how big that table is going to be, we need to figure out how large the data in each of these fields needs to be. Now, in essence, what has to go into each of these locations needs to be able to uniquely identify all of the addresses in physical memory. Now, for the sake of this example, let's say we have 1 gig of RAM. Now, 1 gig of RAM divided into pages, because again, we don't work at a byte level, we work at a page level, is going to be 2 to the 30 divided by 2 to the 12, which is going to simply equal 2 to the 18. Okay, so we have 2 to the 18 physical pages in memory, but we want to just simply be able to uniquely identify all of them. So in order to be able to uniquely identify all 2 to the 18 pages, we need 18 bits. So that tells us that for each one of these blocks, we're going to need at least 18 bits per block of space, such that I have enough capacity here, or information capacity, to actually uniquely point to any of the locations in physical memory. Now we need to extend this a little bit, because we discussed this notion of having a valid or an invalid page, both the notion of if there's an X, it's invalid and a page fault's going to occur. So how do we actually test that? Now there are a number of ways you can set that up, and how you maybe allocate a unique bit string to mean that. But the simplest way to go about doing that is we add an extra higher order bit, where that higher order bit is, say, for example, 1 if it's invalid and 0 if it is valid. And we use that to determine whether or not we should page fault or not. And in order to kind of add that extra functionality, we simply add an extra bit. So we basically just add 1 extra bit, and then we have 19 bits for each of those entries. So with this in mind, how much space is this table going to take us? Well, it's easy enough to calculate. It's simply 2 to the 35, that's the number of entries, times the size of each entry. Each entry being 19 bits. So 2 to the 35 times 19 bits is a small sum of 81 gigabytes. Now, that's an impressively large table. And what's also more impressive about that is that, generally speaking, very few of you will have that much RAM on your system, unless you have some kind of server system. And even if you had 100 gigabytes of RAM, it would make no sense to be utilizing 80% of that space just for that table. Even if you were, for example, to store that whole table on a hard disk, for example, which would make things very slow, that's a considerable amount of space that you're sacrificing. So it's a clear problem with single level paging, and we need to figure out how to avoid that. Luckily for us, there's a simple kind of way of fixing this problem, and it's by doing what we refer to as multi-level paging. But it only works under certain kind of situations, which we'll get into now. So what is multi-level paging? Or what's a multi-level page table? Now, The idea being, instead of having one page table lookup, we have multiple chained page table lookups. By that I mean that we have one page table that we make a lookup in, and what is inside one of those entries points to the next page table. And from there, we actually get the location to the physical page. So we kind of add a level of indirection. So let's look at an example to kind of make things a little bit more concrete. Let's assume we have a 32-bit virtual address, and we're wanting to use multi-level paging. Now we're kind of stuck utilizing 12 bits of that 32-bit address to represent the offset because we have 4K pages. So remember, once again, 4K is equal to 2 to the 12. And now we have another 20 bits to play around with. So you could use a single level paging system and have a page table with many, many entries. So basically it would be 2 to the 20 entries. So it's still very, very large. Or we can use this multi-level system where we allocate 10 bits to be the lookup within the first page table layer, another 10 bits for the second page table lookup, and then we use the large last 12 bits for the offset. So what actually is happening here? Well, we take those first 10 bits, and basically what will happen is it's going to tell us where in this table we should look. So say, for example, the corresponding value of those first 10 bits is this 3. What we'll then do is we'll say, okay, cool, we're at this location. Which of the second level page tables does this field point to? So maybe it points to one over here. And once we've moved to that layer, we now need to decide which one of the entries we're interested in that table. That's where we use the next 10 bits. So those next 10 bits will say, okay, maybe you need to be at location 4. And now we're interested in this block. So now we use the first 10 bits here, the second 10 bits here, and then this will point us to a physical page on the system. And what we now do is we use the last 12 bits for the offset. So we simply add that to the address that is pointed to from this location. Now, this approach in principle is relatively straightforward, but it doesn't immediately tell us why it uses less space. Because in the worst case scenario, if our program was very large and was using the full capacity of our virtual memory process model, it would probably take up slightly more space. So how are we suddenly saving? Well, the trick in this approach is that if I am not referring to a table from the second layer, so say, for example, I don't at any point refer to this table. So here there's a pointer to it, but let's say I at no point referred to this table. It means I don't have to store this table in memory at all, which means suddenly I've saved a whole 1,024 entries that I don't need to save. And this holds for all of the second level page tables. So the more sparsely populated my virtual memory process model is, the more space I can save. And the most common situation is that you don't use very much of that virtual process space at all. You only use a small fraction, which means it's actually quite easy to save significantly with space. Now, this benefit is kind of magnified when you have multiple layers. You can kind of see that just from a simple kind of tree structure. Again, this is a simplification, but even if you just consider a binary tree with a couple of layers, if, for example, I realize that this node is no longer important and I chop off all of the subtrees, it saves me a considerable amount of space. Now, in the case of this example, your tree is not simply binary. In this case, you would have a branching factor of 1,024, but the principle stays the same. By not needing a higher level node, you can save considerably with space that you don't need to store. So that's the big advantage of using multi-level paging. Now, there is a trade-off that happens here, because you're saving on space, but there is a kind of computational cost that can occur because you now don't go directly from virtual address space to physical address space with one table lookup. You may have to do multiple table lookups. Now, in practice, they're actually very fast to implement, but there is a trade-off that if you have many, many lookups, it can slow things down. So there is a trade-off happening that you have to be kind of mindful of, I suppose, if you're designing an operating system. It's not as meaningful as it once was, but it's not completely negligible either. So now that we have this in mind, how does Linux decide to implement multi-level paging? Well, Linux actually uses a 4-layer system where each page is once again 4K in size, And we have an address space that is of 8 bits, or sorry, 8 bytes in size, so considerably larger than our earlier example, which only had 4 bytes in size, which was 32 bits. We now have a whole 64 bytes available to us. Sorry, 64 bits available to us. And what was decided upon in Linux is that each page table is going to hold 512 addresses, which means we need to actually have 9 bits to uniquely identify each of those 12 addresses. And what was decided in Linux is that instead of using all 64 bits to address memory, we're rather going to use only 48 bits. So this was a design decision, largely because at the time and even still now, 128 terabytes is a considerably large program and unlikely to be exceeded. So it was a fair design decision to make. But something you'll immediately note here is that 2 to the 24 is actually 256 terabytes. But earlier we said that the Linux process model is only 128 terabytes. So why is there a disparity? Well, it's because the higher order bit, so if I've got my whole sequence of 48 bits, so the 48th bit, or at location 47, is utilized to indicate whether we're going to be working with a normal page or a kernel page. So we actually use this higher order bit to indicate what type of page size we're going to work with. Now what was discussed here is just a normal page of 4K, but we'll deal with the alternative case shortly. But that's why there's this distinction, that we actually only use the 47 bits of this to actually address the virtual memory. So this is how the page layout is done. So basically the most significant bits are pretty much used for alternative means. So here we say it's unused, but in principle they could be used for chaining of addresses or more complicated actions, but for the moment just assume that they aren't actually used by a program. We generally don't have to concern ourselves with it. And then we have our 4 page levels. So we have page mapping layer 4, 3, 2, 1, and once we've gone through all of these layers of indirection, so we basically did a lookup in this table to find where to look in this table, we did a lookup in there to find where we need to look in this table, and so forth. Finally, at this endpoint, we'll get our physical address, and then we add to it our offset. Now, just to kind of make things easier for you, you'll see that these layers have got specific names in Linux. They're generally kind of arrived at from a historic angle. However, for our purposes, you don't need to worry too much about those names. You can simply think of it as being layer 4, layer 3, layer 2, layer 1. Now, just as a heads up, is that this is 4, 3, 2, 1. We do process this in a left to right fashion, in that I do my first lookup in the highest order bit lookup. So I'll first be looking at page map level 4, then 3, then 2, then 1. So don't get confused and try and do it the other way around. Now, how do we deal with those larger pages? So I mentioned that the kernel has 2 page sizes. It's the 4K and then the 2 megabyte version. And the 2 megabyte version is what's used by our kernel. So how can we tweak our current system to actually handle this? Well, actually, we can do it quite naturally, because you will see here that for this layer, we have 9 bits. And for this layer, we have 12 bits. And 9 plus 12 is 21, and that's precisely what is needed in order to actually uniquely identify all of the pages inside, or sorry, all of the bytes within inside a 2 megabyte page. So in essence, what would happen is that there would be a higher order bit set to indicate that this is a kernel page, and when that happens, we end up using a larger chunk of the address space as the offset. So the same kind of system is used for both of the pages. And we figure out what kind of page we're looking at using this higher order bit. Now, the other layers here, for example, 4, 3, and 2, in principle, though they're 9, 9, and 9, nothing would actually have stopped us doing something like having them of 8 bits, 10 bits, 10 bits. In principle, the system would work fine. It was just a design decision that was made for Linux. But the 9 at the lower level has a big upside in that it allows us to easily store a full offset for a kernel page, which is 2 megs in size, as opposed to the normal small 4K version. Now, you might be wondering, how slow is this lookup actually going to be? I mean, in principle, we could implement all of that in a higher level kind of context, but the upside is that the CPU actually helps us quite a bit, in that there's a specific piece of cache reserved for this kind of translation, which is called the translation look-aside buffer. And basically the TLB operates like a hash table. So the key would actually be the virtual address, and the value that is matched to that key would be the physical address space, from which you can add the offset that you have. The problem with this approach is you're obviously limited in how many entities you can kind of have pre-computed and stored in the translation look-aside buffer. But in practice, even if you don't have a very large TLB, simply having one gives you a significant performance boost. In the same way that simply having cache available to you has a big performance boost, because cache is going to be faster than just RAM. Now, how much of the space do we actually have available to us? It depends largely on the architecture you're actually working with. If we consider a relatively old system, so if we consider an Intel i7 from the first generation of i7, so this is relatively old at this point, I think about 2009, level 1 cache, so that's the closest to the CPU we can kind of get before we actually dealing with registers, would hold 64 small page translations. And level 2, which is still fast but not quite as fast as level 1, would hold 512 page translations. So though it's not that many, it still gives us a significant improvement in speed. And again, as with an all cache kind of operations, we still have eviction strategies and things like that. We'll discuss that in the theory material a little bit more when we discuss how caching is actually implemented. But for the moment, it's enough to know that there's a specific type of cache reserved for this type of translation, which makes lookups really quick when I'm actually trying to do this conversion. And generally speaking, it's such that the actual translation takes about half a clock cycle, which means in essence it's basically free for us because we cannot perceive the difference in performance. So if you're kind of trying to understand how fast a program is, or trying to optimize, you don't need to worry about this backend feature too much. It doesn't have that much of an impact on us. There are situations where you can write code that is a little bit more cache coherent, in that it is a little bit more aware that you want to try and reduce the number of cache misses. So that's a situation where you'd have to load data from a slower kind of bit of memory. The same thing applies with the translation look-aside buffer, but that's the kind of considerations we'll consider in a more holistic context of caching in general, not just the specific case. So now we can start getting into kind of the crux of assembler programming, which is the concept of a register and how we can actually utilize the register. Now, even though you don't normally directly interact with registers in your high-level languages like C++ and the like, fundamentally every program that you write will at some point be utilizing the registers. And by some point, I mean virtually during the entire run of your program, you will be utilizing many registers to do simple things. Certain registers are always used, for example, to build and display stack frames, which are necessary for function calls, amongst a numerous number of other things. You basically actually cannot do anything without having some level of register utilization in a program. So what is a register from our perspective? Well, a register is in essence a small bit of memory, a very small amount of memory, and we'll see we only have a finite amount of registers to work with, that is incredibly close to the CPU. In essence, it's basically part of the CPU itself, and it has the lowest latency to the actual CPU that is possible. This means that if I am to perform an operation between two registers, so say I want to move a value from one register to another, it will always be completed in under 1 clock cycle. Whereas if I want to move something from main memory into a register, that could take considerably longer depending on where that piece of information is. So just to maybe give you a little bit of scale and kind of a context on what it means for something to take a clock, or how much of a hindrance it can be if an operation takes longer than a single cycle to complete. So computer main memory, so this is your RAM, has a latency of roughly about 80 nanoseconds. Some of these times have obviously tightened over the years, but I think the relative scales are still very much appropriate. So main memory has latency about 80 nanoseconds, and a 3.3 gigahertz CPU uses approximately 0.3 nanoseconds per cycle. So that tells you that every 0.3 nanoseconds a cycle will complete, which means 1 clock will have elapsed. So if, for example, I said earlier that you could complete, say, a register to register move in under a clock cycle, it means that we're actually able to perform that operation in approximately 0.3 nanoseconds on a 3.3 gigahertz CPU. Now, memory latency is about 240 cycles, and you can calculate that simply from the fact that it's 0.3 nanoseconds per cycles, and it takes about 80 nanoseconds. Now, that's a lot of cycles from you saying or asking the CPU to perform some kind of calculation. So say you tell the ALU add these two values, and now it has to wait 240 cycles just to get that value into that register. Now, that's obviously a big cost because I could have performed another 239 other operations while I was waiting for that memory to get back to me. Now, the cache is a little bit of an intermediate from main memory in that it's smaller than main memory, but it's closer to the CPU. Now, we generally have 3 levels of cache. There are some more exotic systems that have a 4th level. And generally speaking, level 1 is the cache that is the closest to the CPU and the smallest. So level 1 is the smallest memory and is closest to the CPU and is the fastest. Level 2 is basically a slightly larger cache, but it is unfortunately slightly slower. And again, level 3 is even slower than level 2 and level 1, but is considerably larger in size. Now, if we're in a situation where the bit of memory I wanted to work with was in my level 2 of cache, then on average we'd be waiting about 12 cycles because the latency is on roughly about 4 nanoseconds. So 12 cycles is obviously not nothing, but it's considerably better than 240 cycles. If the data we're looking for is not in level 1, we therefore have to look at level 2, and in that situation it will only have a latency of 39 cycles. Again, worse, but definitely not quite at memory latency kind of speeds. Lastly, if we don't find something in level 2, our last cache option at least is level 3, and here we see that the latency results in us taking about 150 cycles to get the data. So not that much better than main memory, but it is significant or sufficiently better than main memory to actually warrant the actual use in your system. Now, that's all great and well that we have this kind of hierarchy where we have kind of the very slow, and then we have different levels of speed. So you can say, for example, that level 1 would be fast, level 2 is not so fast, and you can even say level 3 is slow. But here comes where, or this is where the register comes in, is that the register is so close to the CPU that there is basically no latency, in that I can perform operations in a single cycle. So I'm not worrying about this load time to get the information I want to the CPU. What this tells us is the more calculations I can perform solely with registers, I'm able to actually achieve significant improvements in speed because I'm not waiting on memory. Now, obviously, any reasonable scale program is not going to be able to run everything just using registers. You need to utilize more memory than just these registers. But it is something when we talk about high performance computation that you'll see there's benefits of actually trying to maximize register utilization where appropriate. So what registers do we have available to us? Now, luckily for us, we're working in x86 assembler, which means we have a considerable amount more registers available to us than you would have had in the 32-bit and the 16-bit version of x86 assembler. So we have a lot more leeway. And on our x86 64-bit mode CPUs, we have 16 general purpose registers, which we'll be spending a large amount of our time working with in this module. We then also have 16 specialized registers. These are called floating point registers, and we indicate them here with the mnemonic XMM0 all the way up to XMM15. This will come up much later. There's also larger versions of this, depending on whether you're talking about AVX instructions or the more specialized versions of them. There is also a different way of dealing with floating point numbers in assembler, which is via a floating point stack. The two modes, so mode 1 and mode 2, are in many ways kind of linked, but for the purposes of this course, we're going to be using mode 1 exclusively when we talk about floating point numbers. Still quite far along in the syllabus, but we're going to focus explicitly on using that version of the floating point register because it allows us to perform vectorized computation. So it's a way of performing multiple operations in a single instruction. So it's what we call SIMD instructions, but we'll get to that later. But I bring this up because if you're curious and you're going further ahead than the textbook, don't spend your time figuring out how the floating point stack works because we're not going to be using it in this course. We're going to use the more modern approach. So we're going to be using 1 and not 2. All our general purpose registers, because we're in 64-bit mode, hold 64 bits of data. The floating point registers obviously have a slightly larger range. they can hold either 128 or 256 bits. That looks a little bit odd at the moment, but it's actually because we stack multiple floating point numbers together to try and, or into one register. But again, don't worry too much about this until we get a little bit deeper into the textbook. But I just want you to be aware that we do have floating point registers at this point. The CPU also has a 64-bit instruction pointer. This is called RIP. This actually dictates or contains the address of the next instruction to be executed. Generally speaking, we will not explicitly alter this register, though you can inspect it as you're running. It is possible to directly alter it, but it's surprisingly difficult to effectively change your jump paths by just altering a RIP register. So it's something that I won't recommend we do, but it is available to us. We then also have some extra kind of registers, which we've referred to as flag registers, or we have a flag register rather. So it's not multiple, it's just one. It's called R flags, and it actually contains status values for various things. Now, the most common kind of status that we'll encounter in this course is, say I compare two numbers. If they are, for example, equal, I will end up setting a specific flag. If one was less than the other, a certain flag will get set, and so on. So we'll actually use flags quite a lot to perform conditional statements. So just if statements, loops, all of those things are going to rely to some extent on flags. There's a whole array of those, which we'll encounter slowly as we proceed through the course. So pretty much at this point, you can think of us having 16 general purpose registers, RIP and R flags at our disposal. Whereas RIP and R flags, we generally speaking don't directly manipulate. We rather simply perform our computations using the 16 general purpose registers. Now, one thing that you have to kind of keep in mind, and it actually is an aspect of assembler programming that makes things a little bit challenging, is that the original instruction set was designed for 16-bit CPUs, and then it was extended to the 32-bit versions of the CPUs, and finally where we are now, it was extended to the 64-bit mode. Now, I bring this up because this isn't a situation where it was redesigned between the 16 and the 32-bit, and then redesigned again between 32-bit and 64-bit. It was very much a situation of we had a certain function set and we bolted on a bit of extra functionality. And then we bolted on another extra bit of functionality again when we did 64-bit mode. So you have a lot of weird properties that if you're working with a 32-bit register, something is slightly different than a 64-bit register and things like that. We will go through those, but it is a common pitfall when working with 64-bit assembler that you might not be aware of some of the nitty-gritty details between the two. It also means you kind of have multiple ways of doing similar-ish things, because when this extension was done, it was decided that backwards compatibility should always be preserved. So this means that even though you were in 64-bit mode, you would be able to execute complete 16-bit assembler. So it was basically to ensure backwards compatibility, but it does mean that we have a lot of vestigial components of the instruction set that are kind of irrelevant to us or might make our lives more challenging than we would like. These old registers, so from the 16 and 32-bit, still have names and still have work, or still work perfectly fine, and you'll actually see we'll make use of some of them to make certain computations a little bit clearer. For example, if I'm talking about an integer in Linux that normally occupies only 32 bits, whereas a long will occupy 64 bits. So sometimes it makes more sense to use the 32-bit register if I'm only dealing with an int, for example. So we'll see that as we go along. The old collection from the 16 and 32-bit era didn't have as many general purpose registers. So we currently have 16. They were restricted to just 8. And to be honest, they were not very general purpose. They kind of had predefined uses, which meant we maybe had 3 or 4 registers we could consistently play around with, and everything else had to be in memory. So we were very constrained with the earlier versions of assembler. Luckily with 64-bit, we have a few more. It makes life a lot easier. The difference between 16 and 8 at first glance might seem kind of negligible, but you'll see very quickly if you write a lot of assembler programming that that's a huge amount of extra versatility by just giving you 8 extra registers, which you'll see as you start writing your code. It helps a lot having a little bit of extra space to perform what you want to do. The 64-bit collection added 8 completely general purpose registers on top of this old 8. So they are still general purpose, the old 8. They have kind of some historical uses, but you're not bound to use them as such. And the 8 general purpose registers have very modern names by comparison, where we simply have R8, R9, all the way up to R15. So there's no equivalent for these registers in 32-bit and 16-bit assembler. And the way in which you simply remember this is it's register 8, register 9, all the way up to register 15. That said, there is no register 7, for example. These general purpose registers simply start from 8 and go up to 15. So you may expect there to be a 7 and 6, but there unfortunately is not. Again, this is a good piece of evidence that the fact that extensions were made to this architecture and instruction set as opposed to redesigns. So how do we identify these registers? So you'll see here I've listed the 8 general purpose registers that we'll be encountering many times. So we have RAX, RBX, RCX, RDX, RDI, RSI, RBP, and RSP. And you can identify whether you're working with a 64-bit, 32-bit, or a 16-bit register quite quickly. If the register starts with an R, it means it is a 64-bit register. If the register starts with an E, it means it's a 32-bit register. And if it does not have an R or an E, and it's just the base part of the register name, it is the 16-bit version of this register. Now, the E stood for extended, so it was an extended register, and R just stands for register. So it's not the most logical naming scheme where we went from normal register to extended register to just register again. But regardless, R 64-bit, E 32-bit. If we don't have that preloaded character, it is a 16-bit register, with some kind of exceptions where we access lower parts of the actual register. But generally speaking, if, for example, the base 64-bit one would say RAX, this bottom component would indicate the lower 16 bits of it. Now, all of these are, in essence, are general purpose in that you can do what you want with them, but they do have kind of historical uses. For example, RAX is often used as an accumulator. So say, for example, you were looping over an array, you were adding all the elements in that array. You might be storing that cumulative sum into RAX. So that's why it's often referred to as the accumulator register. RBX is a little bit more free. RCX is often used as a count register, largely because it has a C in the name. But you'll see this is common convention even in compilers, that if you have a loop, say you have a for loop that's looping again over an array, you're iterating integers. So say, for example, I had for int I, and then if this was decompiled, or disassembled rather, into assembler code, you would see that I'm likely going to have RCX being incremented and used in my comparisons as I'm looping through. So you'll see RCX is often used for a count variable. RDX, again, pretty free. RDI is often used as a destination index. So you'll often see instructions have what we call a source and a destination. So where you're loading something from being the source, and where you're loading that data to being the destination. This will come up more frequently when we start doing more complicated system calls and things like that, but it's a common use that RSI will be used as a source index and RDI will be used as a destination index. RBP is used for a stack frame base pointer. This will become a lot clearer when we talk about functions, so you don't have to worry about this too much, but it's basically used in building the stack frame. And RSP is also used for part of the stack frame, but it's what we call the stack pointer, and this basically indicates how much stack space you have allocated so far. And we also use RSP to explicitly push or pop things off of the stack. Again, don't worry too much about this for the moment. We'll get there shortly of how to actually use RSP a little bit more precisely. But it's just good to know that these are available to us at this point. We also have the ability to access the lower parts of some of the 16-bit registers. And this is largely a carryover from when we had 16-bit assembler. But if I, for example, have the register RBX, it is possible for me to get the bottom 8 bits and the top 8 bits from that register and actually treat them kind of independently. So in that case, BL will be the lower 8 bits of BX, and BH will be the upper part of that as well. So in essence, we have BX sitting like this, and this will be BL, and this will be BH, where this is the lower order bits over here, and this is the higher order bits over here. So you can think of it as being 0, 1, all the way to 7, and then 8, all the way to 15 over here, and this will be encapsulated by BH. And we have the same functionality for AX, BX, CX, and DX, and in 64-bit mode, the extension to this for getting the lower byte is possible from RDI, RSI, RBP, and RSP, where you can basically use the second 2 characters and then you simply append an L to them to get the lower byte. There does not exist a way of getting this equivalent to the higher byte directly from these registers. So obviously RDI is 64 bits, but in this case, say RDI, we can use DIL to get the bottom 8 bits, but if we wanted to get the next 8 bits up from them, there isn't an explicit instruction for it. It is possible using multiple instructions, but there isn't a specific way of doing it. Now, something that I think is very useful is to kind of visualize how things work here. And it's not always immediately clear, but these registers, these upper and lower parts of the registers, are actually linked. By that I mean that if, for example, I'm talking about RAX, EAX is in fact the bottom half of RAX. And by the same token, the AX part is actually the lower 16 bits of EAX. So just to visualize that a little bit, here we have a summary of the sizes and their relationships. So here's RAX taking a full 64 bits. We then have EAX, which is our 32 bits. But this EAX is the same as the bottom of RAX. So if I change something in EAX, it affects RAX. Now the extension again of this is that we have AX, which is the bottom half of EX. And we have AL, which is the bottom half of AX. And AH is the top half of AX. But again, say for example, I went and I changed one bit here. So say I turned a 0 into a 1. That same bit over here would get altered. So by changing AH, I have an impact on RAX. So it's something to always keep in mind is that though you can access different components of this register, they are not independent registers. EAX is part of RAX, and AX is part of EX. AL is part of AX, and so forth. They're all part of the same contiguous bit of space. We get similar kind of functionality with the new general purpose registers that we encountered. So say, for example, I wanted to gain access to the bottom 32 bits of R8. All I would need to do is append a D. So that would indicate that I want a double word. So R8D would give me the bottom 32 bits. R8W, on the other hand, would give me the bottom 16 bits. And if I were to append a B, it would give me the lower byte. So these are all ways in which we can access those subcomponents as well. Now, at first, all of these register names may start feeling a little overwhelming. But the more you work with them, you'll quickly start seeing the relationships, and it actually is very intuitive to kind of keep all in your mind at the same time. But at first, it does feel a little bit intense on memory. Unfortunately, it is a bit of the nature of assembler that you have a lot of instructions and a lot of little esoteric details to remember. But the more you work with it, the easier that will become. So now that we know how registers are kind of formed and how the lower order registers relate to the higher order registers, let's actually try and go through one or two instructions. So specifically, we're going to discuss the move instruction. Moving in assembler is pretty much one of the most fundamental operations that you need to actually be able to use. Something that I think we should maybe clarify before you potentially get lost if you're looking at other sources. The mnemonic that we use for move in Yasm is MOV. And specifically, we're utilizing what's referred to as Intel assembler syntax. I bring this up because if you were to take your C++ code and disassemble it using GCC, you will actually end up getting move instructions that look like this, where you have move Q, move D, move W, and so forth. That is not Intel syntax. That is AT&T syntax, which we do not use in this course. So make sure that you don't get led astray. We're always going to use Intel syntax. It's what the textbook uses throughout. And it's what all the slides will use, and it's what you're expected to use an answer with. So don't get confused if you see that elsewhere and think you're missing something. It's just a different version of the syntax. But we stick to Intel syntax and not AT&T syntax. Now, most instructions are able to actually utilize immediate values of 1, 2, or 4 bytes. So just for context, we generally call a constant an immediate value in assembler. Move, however, is able to move larger immediate values. It is able to move full 64-bit immediate values into a register, so that's a nice upside. And here we have our first assembler instruction that we're going to discuss. We've already done some moves when we did the self-exiting program earlier and also in your pracs. But here we see we're going to move a 64-bit value into RAX, and here we're going to move 0 into RAX. Here we're going to move 5 into EAX, which means I'm moving 5 into the lower half of the register. Now this is where the kind of interesting details about 64-bit assembler happen. If I move a value into an EAX register, the default behavior is that the upper half will be set to 0. What this means is if I have RAX, so let's say this is RAX, and this bottom part was EAX, and this was the extra bits all the way up to bit 63. If I alter EAX, so say in this example I could go and I set this to be the value 5, it will load the value 5 into this register in binary, and it will clear all the higher order bits. It will set them all to 0. That's the default behavior of performing a move like this. And this is a common place where people can make mistakes because they think that the top 32 bits is going to be left untouched. Now, if we look at the next example, you'll see that I'm loading the value 16 into R8W. Remember, W is 16 bits, so I'm loading the value 16 into the bottom 16 bits of R8. So again, we have R8 over here, and from R8 we're going to have the little bottom bit over here, which is going to be R8W, which is just going to be the 16-bit chunk. Now, what's interesting or annoying, depending on how you look at things, is if I load something into R8W. So say I set it to 16 as in this example, I'll end up storing the value 16 in binary, and then the question is what happens to these higher order bits? Your first gut might be telling you, oh, it's going to set them all to 0, like happened in the EAX case. Unfortunately, if you alter simply a word, the lower order word, it will not change the higher order bits at all. This behavior of zeroing out the higher order bits or 0 extending is exclusive to when you move or perform any kind of operation onto a 32-bit register. So it's very specific to acting on a 32-bit register. So it's one of those things to keep in mind, and this is why it's important as well to practice using GDB so that you can check what is actually happening with these registers as you perform your calculations. So let's look at how we can move something into a register that isn't an immediate value. So the next thing we may want to do is we want to try and get data into a register. So we would like to load data from memory. So on the top here we have our data segment defined as we had before. Just in case you're not too familiar with number C, what ends up happening here is that it assigns a byte for each one of these elements. So it will create a data byte for each one of these comma separated entities. Now in this text segment, let's try and understand what's happening here. So the first thing is that we move A into RAX. Now, this is maybe what you would try and do if you hadn't looked online to how to make a move. But what will actually happen in this command is that you won't move the value at A into RAX. Instead, you actually load the address A into RAX. So remember from before that these values over here are our labels, and this might correspond to some kind of actual address space. So this could be some arbitrary address. Now we interact with it and refer to it in our code by simply using A, which is the label. But by moving A into RAX, all I'm doing is I'm loading in the address of A. not the value of A. You can kind of think of this as similar to in C++, where RAX here is in essence holding the pointer of variable A. So it has the address that would contain the value 120 or 175, but it is in itself not the value, it's simply the address. If I actually want to gain access to the value at address A, I have to use this bracket notation over here. You can kind of think of this as dereferencing. So it takes A and it dereferences it and gives us the value that A was pointing to. So this is why I mentioned earlier that we basically always work with memory as if it was stored as in a pointer. Here we see that I'm going to move C into RCX, and now this is where you might be getting a bit confused because I'm dereferencing, so that's fine. I know I want the value, not the address, but C points to this 1 so long. So basically it will have the value 000 1 stored in the first byte. But what will actually happen here is because I'm moving into a 64-bit register, even though the first element here is just this 1 and it is stored in a byte, I will actually load in 8 bytes or 64 bits, which actually means this whole sequence will get moved into RCX. Now, this brings up an important lesson, is that in this example, DB had 8 elements. C had 8 elements, each being of 1 byte in size. So we could perfectly fit all of this data into RCX. It'd be hard to use the data in that form, but I mean, all of it is in principle stored into RCX. The question is, what would happen if I didn't have this 8th element? If I only had 1 through 7. Now this is where you can make mistakes with assembler very easily, because what will happen is it will load all of these 7 elements in, as well as the first couple of bytes of D. So in this case, it only needs 1 more byte, so it will load one of the bytes from the next element. So it's easy to overload past where you think it is. So say, for example, you were loading something that was just a byte, but you make a 64-bit move, it will always extract 64 bytes. The same thing happens if I'm moving into memory, which means I can accidentally overwrite things I don't want to overwrite. So you have to be very conscious of sizes when working with assembler. Here, the last example, I'm simply moving D into EDX, and that's just an example of me loading a 32-bit value into a 32-bit register. So let's look at our first slightly more complicated program than our self-terminating one and our hello world. So here we have a data segment again with 2 elements, A and B. They're both DQ, so they're data quad words, so they're 64 bytes, so it should be easy to work with. We want to write a program that's just going to add them together and return. So what we do over here is I'm going to load A into RAX. Again, I'm loading the value of A. Then I'm going to use the add operation, which is going to add what is stored in RAX with RBX and put the result back in RAX. So it will take what's in RAX, add it to RAX, and add B. So, sorry, I may have misspoken there. So in essence, you can think of RAX or this operation performing the following. So in this situation, the left-hand operand is going to actually be our destination from that operator. You don't need to worry too much about the XOR and RET at the moment. In essence, XOR in RX sets RX to 0. I'll cover that shortly, and return just returns from the program. You'll see that the textbook's example here uses main, so this would have been linked using GCC. Just thought I'd mention it. We won't need to worry about that at the moment, but just in case you were unclear of where that came from. Now there's 3 more instructions that I think are important with regards to moving to discuss, and they're referred to as sign extend or zero extend instructions. Now I mentioned earlier when I made a move of a value into a 32-bit register that by default it would zero extend. Now the truth of it is it's slightly more subtle than that, in that if I move a double word into RAX, the upper half is zeroed out, as I said, but if you move a 32-bit immediate value into 64-bit register, it is actually sign extended. So what does that mean? What does sign extend mean? So what sign extend means is that, say I had a 32-bit negative value. That would mean it would start with a 0, and it may have a corresponding bunch of other bits, because we represent negative values using 2's complement. Now, if I were to move that value into a 64-bit register and the top order bits were set to 0, so all of these were suddenly set to 0, this value over here's sign would have changed. It no longer represents the same value. But what if I want to store a 32-bit value into a 64-bit register and make sure that its sign is preserved, so it actually still means the same thing? See, if the value was positive, this 0 situation wouldn't matter because we simply do our conversion with the low order bits and it would match our expectation because it was a positive value. But in order to make sure that, say, -7 is still -7 once moved into a 64-bit register, we'll need to sign extend. And all that means is that instead of always copying zeros up the higher order bits, we simply propagate what the higher order bit was. So if the highest order bit here was a 1, we simply make all of the higher order bits all the way to 63 be a 1 as well. And now what actually ends up happening if you do the 2's complement calculation, you'll see that we've actually made sure that the value is still represented as the same. So if, for example, this higher order bit was a 0, which meant it was actually a positive number, then we would only extend it with zeros. Even if we enabled sign extend, it would simply extend the higher order bit. So it's something to keep in mind when we start doing some kind of arithmetic operations, that if you have negative numbers, you have to be very aware of whether or not you need to sign extend if you're pushing them into a higher or a larger size register. So the question is, how do we actually control this operation? So you can rely on what is done by default. So if I'm loading something that's a value into a 32-bit register, it's easy. I say, okay, fine, it's just 0 extended. I don't need to worry about that. Maybe that's what I want. But what if that's not what I want? How do I actually get around doing something like that? So say I have some data and I want to load it into a 64-bit register, but I want to ensure it's sign extended. Now, the way in which you do this is you use the operation move SX, sign extend. So the S is for sign and the X is for extend. I specify the bit of memory that I want to load into the register. But there's a little bit of extra information happening here. Normally, I don't specify the size. But in this case, because I want to load data into RAX, and let's assume for this example that data is in fact 1 byte in size. So it's a label to something in memory. So it's basically sitting in our data segment looking like this, dB, and say the value is -7. I want to load this into RAX. So I use sign extend to ensure that in RAX it still actually represents -7. But I need to actually tell the assembler how much data is at this location, because the assembler doesn't keep track of how much or what size I specified it is. All it knows about data is that it has the address for data. What I do with that is up to myself. So if I want to explicitly say that I want you to only load 1 byte from data and move it into RAX, I have to actually state the size. And in that case, in this example, I need to specify byte if I'm trying to move a singular byte into RAX and sign extend the value. Now, there are different versions of this, but something I just want to maybe make clear is that these operations, the way you can remember if you have to specify the size is you only use them if there is no way for the instruction to have actually implicitly known what size the information you're referring to is. So in this example, if I interpret this command, okay, all I can tell, say I didn't have this byte specified. I want to load a value that is at address data into RAX. Okay, great. Now, RAX is 64 bits, so maybe it would be 64 bits, but I'm using sign extend, so that tells me it can't be 30 or 64 bits. So that means that what's in data, 32 bits, 16 bits, or 8 bits. But how do I actually determine which of those it is? I can't. It's not possible for the assembler to figure that out, so I need to tell it that it's a byte. We can kind of use a similar notion to use the 0 extend operation. So say, for example, I want to load a word. So a word is 16 bytes into RBX, a 64-bit register, but I want to ensure it's 0 extended. All I have to do then is say move ZX and then specify the size and provide the name. Now again, something to consider here is, say I didn't have this instruction and I wanted to load sum into RBX. What could I do? Now, if I just try to execute something like this, move RBX sum, and sum was defined in my data segment as a data word with some kind of value. When I execute this command, because the register on the left is 64 bits, regardless of what true size sum is, this instruction over here is going to load 64 bits from memory, which is not what we want, because then it's going to load kind of data past this instruction, or this bit of data, which is not what we wanted at all, which is why we're kind of priced into specifying it with a more exact instruction. So I have to specify move ZN because I want to 0 extend, and I'm only caring about a singular word from that address. There's also extension to these operations, which is the move SXD. This stands for move sign extend double data word, and this is specifically for situations where I want to move a double data word into a 64-bit register. Now here it can be argued that this D word is a little bit of a redundant one because it's kind of specified in this instruction, but generally the rule applies that if the assembler can't implicitly figure out what is happening, you definitely need to specify the size. Now the question you have to ask yourself is there a ZX version of this? So is there a move ZXD? And the answer is there isn't a move ZXD, because by default, if I were to move a 32-bit value into a 64-bit register, it would automatically 0 extend. So I don't need a specific instruction for that. Now, we've moved from a piece of memory into a register. How do we move back? So how do I go from a register to memory? Pretty much just swap the order of the operands. So we change the destination to in fact be the memory location. So I want to, in this instruction, save RAX at location A. And again, I simply use the D reference to indicate I'm changing the value at address A. If you tried to write an instruction like this, the assembler will simply yell at you and tell you that it's not an allowed instruction because you cannot change an immediate value. Basically, it says, well, you can't change the constant A, so it won't let you do that. And the amount of data that is stored into memory is dependent on the register size. So in this first case, it will move 64 bits into A, so the whole of RAX. In the second case, it will load 32 bits into RB or into B. So the whole register will go into B, but it'll move precisely 32 bits. Number 3, we'll load a whole word into C, so only 16 bytes. And then lastly, because this is a singular byte-sized register, I'll only load 8 bytes into D. Now again, if for example, I was in a situation that my memory was defined as follows, where A wasn't actually 64 bits and it was less. So let's say A was a data byte, can have any value. B was, say that was correct, it was a double data word, and D was a double data word. What would end up happening if I made this move? So move number 1. I would load 64 bits into A, and it would fill this whole byte, so it will be nice and full with data, but it will keep filling further down. So we'll start affecting B, and even a little bit of C, because this instruction over here is always going to load 64 bits into that address. So you have to be very careful that your sizes match, otherwise you'll get a lot of bugs, and sometimes the bugs are very hard to debug because the program doesn't break as such, you just start getting very incorrect answers. You can also obviously move register to register. The caveat here is the register sizes have to match. So I can't move from EAX into RAX, for example. I need to move from like to like. So I can move from, say, RBX to RAX. Same thing, I can move from ECX to EX and so forth. I can also move from the lower order bits, so I could move from AL to CL. Again, you'll see this little trick with the 32-bit registers, in that if I'm moving a 32-bit value into a 32-bit register, it will 0 extend the higher order bits. So after this operation, the higher order bits of RAX have actually been affected. So again, be very careful that when I move anything other than an immediate value into EAX, it's going to 0 extend. But even if it was an immediate value, it would sign extend and it could still corrupt the higher order bits. So the trick is, if I move something into a 32-bit register, I unfortunately affect the higher order 32 bits of it as well. So again, even if I'm only moving into this chunk of RAX, which is EAX, I'm actually going to affect the whole of RAX because I'm going to end up zero extending all of these bits. So you need to make sure that's the behavior that you want when working with these registers. So it's always something to keep in mind. Again, if you're not sure of what the behavior is, maybe you think maybe this is an ambiguous case and not certain, your best bet to figure out what's going on is to use GDB to see what's actually in that register after each instruction you execute. So always keep that in mind. Much like anything with programming, your best means of figuring out what's going on, if you're not sure from just the theory alone, is to try it out. And that way you can kind of experiment and see what's happening. Sometimes if a specification is not that clear, try it out and it'll make it clear very quickly. I highly recommend doing that with assembler programming in particular. So that brings us to the end of the second assembler lecture. From the next lecture, we're going to start doing kind of a little bit more computation. So we're going to start going through the addition, subtraction, multiplication, those kind of operations. So we can start doing slightly more interesting assembler programs.